Namaste all. Welcome back to Sankalp Learning, second PUC Chemistry, Unit 1 Solutions. In yesterday's session, you would have studied till solubility, right? I'm going to continue today with Henry's law. A quick recap of yesterday's session. We studied what is solution and that what is solvent and what is solute, what is binary solutions. Then we have also seen the types of solutions, which is gaseous solutions, liquid solutions, and solid solutions. Then we have also seen the different ways the concentration of solutions. And we moved on to solubility and the factors affecting solubility. Then solubility of solid in a liquid. Also, you studied what is saturated and unsaturated solutions and effects of temperature and pressure on it. Then solubility of gas in a liquid. Again, effect of pressures and temperature on it. Today, we are continuing with Henry's law. What is Henry's law? Have you ever heard what is Henry's law? Okay, let's begin. Who was Henry? Henry was the first to give a quantitative relation between pressure and solubility of gas in a solvent, right? And that whatever relationship between those pressure and solubility that Henry gave is just termed as Henry's law. What does it states? Let's see what is the statement of Henry's law. Please make sure that you see this, you learn this Henry's law properly, and you should not get confused with Henry's law and Raoult's law, which you are studying in further slides. Let's see what is Henry's law. This law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of a liquid, or you can also just say a solution. Okay, I'll read it again. Please make sure that you concentrate what is Henry's law. At constant temperature, temperature should be constant at this case, the solubility of a gas in a liquid is directly proportional to the partial pressure of a gas present above the solution. Okay. This was the statement which was given by Henry. Also, Dalton, he added some contemporary of Henry. Okay. What he again told us, they actually combined and gave one statement which is shown here. There's no need to remember this name as a just extra information. I'm giving his name, Dalton. Okay. This Dalton added some extra layer on top of Henry's law. What was that, Andra? He defined in terms of mole fraction. Mole fraction prakara, he defined what is the solubility of a gas in a liquid. Okay. Here, what he told us, mole fraction of gas in a liquid is proportional to the partial pressure of a gas above the liquid or solution. Just he took a relationship between mole fraction and partial pressure. That's all. Okay. So when you combine these two statements, again, Henry's law was modified as the partial pressure of a gas in a vapor phase is proportional to the mole fraction of a gas in a solution. Okay. In simple words, how we can tell is P, which is partial pressure of a gas in vapor phase. Okay. It is proportional. First, let me consider a proportional symbol. Is proportional to the mole fraction of a gas. Mole fraction of the gas is just X. Okay. Let me write this in a new page. Yeah. Oh, initially, partial pressure was directly proportional to what? Mole fractions, right? As it was Henry's law, this mole like proportionality symbol was replaced by proportionality constant or Henry's constant called as KH. Okay, KH into X. This is a standard Henry's law. So please remember this, it is important. Next, let's see what are the important points regarding Henry's law. See, let me show you one graphical representation. If we draw a graph between partial pressure, okay, let me take your partial pressure. Partial pressure of the gas at the y-axis, and in x-axis you will be plotting mole fraction. Okay, mole fraction here. So when you plot these two, as they are proportional to each other, if one increases, other also increases, something like this. It is linear in nature, okay? So in simple words, if we draw a graph between partial pressure and mole fraction of a gas, then we should get a plot like this. And remember one important point. If the KH value is high, if KH value is high, solubility will be low. Okay, just remember this. Higher the KH value, lower the solubility. Please note this point somewhere. If KH value Henry's constant is high, solubility will be low. And yeah, let's go through the important points of Henry's law. Different gases, have different KH values at the same temperature. Okay, that is K depends on the nature of gas. Based on nature of gas, KH value vary ಆಗ್ತಾ ಹೋಗುತ್ತೆ. So remember this point for different gases. Different gases ಗೆ ಬೇರೆ ಬೇರೆ. Someone is asking Zoom link. Okay. Yeah, please wait. Our team will share you a Zoom meet link. Okay. Okay. Till then, please concentrate here. Let's see the important points of Henry's law. Different gases have different KH values at the same temperature. Okay. And also, KH value depends on the nature of gases. As I told you previously, higher the value of KH, what happens? Lower is the solubility. Remember this important point? Then KH value of a particular gas increases with increasing in temperature. KH value temperature increase ಆದಾಗ KH value ಕೂಡ increase ಆಗುತ್ತೆ. But KH value increase ಆದಾಗ solubility decrease ಆಗುತ್ತೆ. Please remember this relationship. Okay. Then it indicates the solubility of a gas decreases with increasing in temperature. Again, let me give you a short point here. Remember the value increases with increase in temperature. Okay. And if KH value increases, higher the KH value, lower the solubility. So you can remember it as also nodi illi KH value increase ಆದಂಗೆ solubility decrease ಆಗುತ್ತೆ ಅನ್ನೋದು ಒಂದು ಪಾಯಿಂಟ್ ಓದಿದ್ರಿ. KH value increase ಆಗ್ತಿದೆ ಅಂದ್ರೆ of course temperature increase ಆಗ್ತಿದೆ. So again these both are interlinked. How? Increase in temperature leads decrease in okay. So remember this point. They'll ask you in some twisted way just for 1 mark. So next, let's see the applications of Henry's law. Henry's law ಎಲ್ಲೆಲ್ಲಿ apply ಆಗುತ್ತೆ? Of course, soda drinks, which we drink generally. In that soda drink, ಏನ್ ಮಾಡ್ತಾರೆ? To increase the solubility of carbon dioxide gas. Carbon dioxide gas na, like usually soft drinks ಅಲ್ಲಿ carbon dioxide ಇರುತ್ತೆ. That carbon dioxide na ಜಾಸ್ತಿ soluble ಮಾಡಕ್ಕೋಸ್ಕರ bottles na high pressure ಅಲ್ಲಿ seal ಮಾಡಿರ್ತಾರೆ. So again, this is the point where Henry's law is being applicated. Okay, I mean applied. So Henry's law is applicable in soda, I mean soft drinks or soda water. ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತಾರೆ? Carbon dioxide ಜಾಸ್ತಿ ಮಾಡಕ್ಕೋಸ್ಕರ they are high sealed in under a high pressure. Okay. Remember this one thing, and you know what is scuba, like scuba diving, right? There what happens? Usually high concentration and dissolved gases irutte alli, also high pressure irutte. ಈ ಪ್ರೆಷರ್ ಎಲ್ಲ ಜಾಸ್ತಿ ಆದಾಗ ಸಾಲಿಬಿಲಿಟಿ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. ಅಲ್ಲಿ ವಾಟರ್ ಒಳಗಡೆ ಇದ್ದಾಗ ಡಿಫ್ರೆಂಟ್ ಪ್ರೆಷರ್ಸ್ ಇರುತ್ತೆ. ಅಂಡ್ ಆ ಸ್ಕ್ಯೂಬಾ ಡೈವರ್ಸ್ ಮೇಲೆ ಟಾಪ್ ಲೆವೆಲ್ಗೆ ಬಂದಾಗ, ಇನ್ ದಟ್ ವಾಟರ್ ಟಾಪ್ ಲೆವೆಲ್ಗೆ ಬಂದಾಗ, ಅಲ್ಲಿ ನಾರ್ಮಲ್ಗೆಲ್ಲ ಬಂದಾಗ ವಾಟ್ ಹ್ಯಾಪನ್ಸ್ ಇಸ್, ಕೆಳಗಡೆ ಹೋಗಿದ ತಕ್ಷಣ ಒಂದು ಅಡಾಪ್ಟೇಷನ್ ಇರುತ್ತೆ, ಮೇಲೆ ಬಂದ ತಕ್ಷಣ ಅಗೇನ್ ಚೇಂಜ್ ಆಗ್ಬೇಕಲ್ವಾ ಬಾಡಿ, ಲೈಕ್ ಬ್ಲಡ್ ವೆಸಲ್ಸ್ ಎಲ್ಲ ತಗೋತಿರೋ ಅಮೌಂಟ್ ಆಫ್ ಗ್ಯಾಸಸ್ ಚೇಂಜ್ ಆಗುತ್ತೆ. ಅಟ್ ದಟ್ ಪಾಯಿಂಟ್ ಆಫ್ ಟೈಮ್ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ನೈಟ್ರೋಜನ್ ಗ್ಯಾಸಸ್ ಎಲ್ಲ ಹೋಗ್ಬಿಟ್ಟು ಲೈಕ್ ಬ್ಲಾಕ್ ಮಾಡಿಬಿಡತ್ತೆ ನಮ್ಮ ಬ್ಲಡ್ ವೆಸಲ್ಸ್ನ. ಸೊ ವಾಟ್ ಹ್ಯಾಪನ್ಸ್, ಅಲ್ಲಿ ಬ್ಲಡ್ ಕ್ಯಾಪಿಲರೀಸ್ ಎಲ್ಲ ಬ್ಲಾಕ್ ಆಗೋದ್ರಿಂದ ದಟ್ ಲೀಡ್ಸ್ ಟು ವೆರಿ ಲೈಕ್ ತುಂಬಾ ಕ್ರಿಟಿಕಲ್ ಕೇಸ್ ಕಾಸ್ ಆಗುತ್ತೆ, ವೇರ್ ಇಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಬೆಂಡ್ಸ್. ಓಕೆ, ರಿಮೆಂಬರ್ ದಿಸ್ ಬೆಂಡ್ಸ್. ಇದೊಂದು some painful and dangerous to life, which is medical condition. Okay, na? ಅಗೇನ್ ಈ ಬೆಂಡ್ಸ್ನ ಅವಾಯ್ಡ್ ಮಾಡಕ್ಕೆ ಏನ್ ಮಾಡ್ತೀವಿ? ಹೀಲಿಯಂ, ರಿಪ್ಲೇಸಿಂಗ್ ನೈಟ್ರೋಜನ್ ವಿತ್ ಹೀಲಿಯಂ, ಈ ಕೆಲಸನ ಮಾಡ್ತೀವಿ ಟು ಅವಾಯ್ಡ್ ದಿಸ್ ಬೆಂಡ್ಸ್ and the toxic effect like of high concentrations of nitrogen in the blood. The tanks used by scuba divers are filled with air, diluted with helium. So please remember this, helium in the dilute ಮಾಡಿರ್ತಾರೆ ಆ scuba divers the tank. Okay, so this is the place where Henry's law is applied. Quickly, let's move on to the next one. As you studied in previous sessions, you know what is molality, what is molarity. Also, you know the normality and solubility, alva? So quickly and remember these are the important definitions: molality, molarity, normality, and solubility. Okay. So directly let's move on to the Raoult's law. What is Raoult's law? You know what is Raoult's law? Remember, he is a French chemist. Raoult is a French chemist, where his full name is Francois Martin Raoult ಅಂತ ಹೇಳ್ತೀವಿ. Okay. And he gave the quantitative relationship between all the between the binary solutions. I'll let you know what are these P1 and X1. Okay. Let us simply understand this Raoult's law. Basically, let's consider what is binary solution. What is binary solution? As you studied in previous session, binary and the solution containing only two components is called as binary solution, alva? So let us consider that binary solution. Two volatile liquids ತಗೊಳ್ಳೋಣ. And remember, our binary solutions ಯಾವುದಾದ್ರೂ ಆಗಿರ್ಬೋದು. Okay, liquid in liquid ಆಗಿರ್ಬೋದು or solid in liquid ಕೂಡ ಆಗಿರ್ಬೋದು in these two conditions. Let us take two volatile liquids only. Okay. Volatile liquid 1 and volatile liquid 2. ಇದೆರಡನ್ನ we'll be taking in some closed vessel ಅಂತ ಅನ್ಕೊಳ್ಳೋಣ. Then both the components would evaporate eventually and equilibrium. And equilibrium would be established between vapor phase and liquid phase. So in general, let's take P total. P total ಅಂದ್ರೆ ಹೇಳ್ತೀನಿ. Total vapor pressure, what we are considering as P total. P total will be total vapor pressure. Okay. And P1, P2 ಏನಾಗಿರುತ್ತೆ ಆಗ? P1, P2 will be P1, P2 would be what? Partial vapor pressure of both the components, solution 1 and solution 2. I mean liquid 1 and liquid 2 in just one solution. Okay. And P1, P2 ಏನು ಅಂತ ಗೊತ್ತಾಗಿದೆ ಅಲ್ವಾ ಈಗ? Let's move on to X1, X2. X1, X2 you have studied previously. What is that? Mole fractions. Okay. X1 is mole fraction of first liquid. X2 is mole fraction of second liquid. So simply let us move on. You should remember what is Raoult's law so that you can understand why I told you P1, X1 and P total there. Okay. So the relationship is the relationship between these partial pressure and mole fraction is known as Raoult's law, but exact statement I'm going to tell now. Okay. for a solution of volatile liquid, you took volatile liquids, right? So for a solution of volatile liquid, the partial vapor pressure of each component of P1, P2 of each component of the solution is directly proportional towards these two. What are those? X1 and X2 was mole fractions. All right. So how do you state Raoult's law? For a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction. So remember this statement, which is very important again. You have to state Raoult's law. And these relationships I'll tell you in further slides. Okay, as of now, you understand why I told what is P1, what is P2, what is X1, and what is X2. Okay. As per this definition, what do you understand? Partial vapor pressure of each component. Alva. Let us take P1. P1 is directly proportional to its mole fraction. Its mole fraction in the sense we are taking first components, right? So it is X1. P1 is directly proportional to X1. Then when you remove that proportionality symbol, you have to replace with some constant. We'll be considering what? Vapor pressure of a pure component. Okay. So let me take P1 is equal to P1 naught. This is what you're taking here, replacing in proportionality symbol into X1. Consider this as equation 1. All right. Similarly, this is just for one component you have taken. Next component would be what? P2, which is P2 naught into X2, its mole fraction. Again, these two equations should be considered so that you can understand the further explanations. All right. See here, as I told you deeply, what you understood is you understood this, right? P1. What was P1? Vapor pressure of first liquid. And P1 naught was pure components vapor pressure. The next one was its mole fraction. Similarly, you did for P2, X2, right? This is why I gave those explanation for what is P1, what is P2. Okay. So Raoult's law is done basically in basic level, right? That was Raoult's law. So according to Dalton's law of partial pressure, what he did, see, it's here. Of pressure. So Dalton's law of partial pressure, what he told us, the total pressure over the solution phase in the container will be the sum of partial pressures of the components of a solution. So let's see basically what was that. Sum of pressure in the sense what you saw P2, which is total, okay, total partial pressure. This was Dalton's law of partial pressure. When you combine Dalton's law with Raoult's law, you'll be shown here. Okay. Let me show you the final equation. See, in ಹೇಳ್ದೆ ನಿಮ್ಗೆ Dalton's equation was according to Dalton's partial pressure. ಏನಿತ್ತು ಅದು P total is equal to P1 plus P2, sum of partial pressures of each components ಅಲ್ವಾ? When you substitute these values, Henry's law ಓದಿದ್ರಿ, Raoult's law ಓದಿದ್ರಿ. ಆ Raoult's law ಜೊತೆ ಕಂಬೈನ್ ಮಾಡಿದಾಗ P1 ವ್ಯಾಲ್ಯೂ ಏನಿತ್ತು ಅಲ್ಲಿ P1 naught into X1 plus P2 naught into X2, right? This was Raoult's law. So when you simplify this, you'll be getting 1 minus X2 into P1 naught plus P2 naught into X2. Again, what was this X1 minus X2 is? In place of X1, you are putting 1 minus X2. See, in simple words, X1 plus X2, sum of mole fractions is unity. So X1 plus X2 is 1. If you want, see, X1 plus X2 is 1. If you want X1, you'll transpose this, right? So X1 will be 1 minus X2. That is what you wrote here. So final equation will be would be P1 naught plus P2 naught minus P1 naught into X2. This is the final equation for Raoult's law with Dalton's. Okay, so let me show you that. See, this is the equation. This is the equation which I showed you just now, which is P total. Okay, here they are given as A and B, where I have shown you as 1, 2. Okay, for first component and second component. Next, let's see the limitations of, before going to that, you understood, right, what is P naught A? A in the sense I showed you as P naught 1, I mean P1 naught. So this was P2 naught, this was P2. Okay. So vapor pressure of component A, vapor pressure of component B, and vapor pressure of component again in pure state and in a solution aste. If you are getting naught, it is a pure state anta artha. Next, limitations of Raoult's law is applicable only to very dilute solutions, and it is applicable to solutions containing non-volatile solute only. Solute should be non-volatile, whereas solvent should always be volatile. Okay. That is not applicable to solutes which dissociate or associate in particular solution. I'll tell you what is dissociate and associate in further slides. Detail, okay? As of now, let's move on. Yes, you have something called as ideal and non-ideal solutions. Yeah, I'll show you next slide. I'll tell you in general, in perspective of Raoult's law, okay? We'll be plotting P1 versus P2. Like this. P1 naught, P2 naught. Then you have something called as X1, X2, and you have X1, X2. Here it is mole fraction, and here it is vapor pressure, Raoult's law. Okay. You just see this. This is a plot of P1 versus P2, the mole fraction X1 and X2 for a solution, which gives a linear plot. See, which is given here is linear plots. All right. And this above full line is what? P1 plus P2. It is P total. Okay, Dalton's law. See, this dotted line and this dotted line. What do they show? They both pass through the points which X1 and X2 are equal to unity. Okay. And this plot, this complete line is, as I told you previously, it is P total. This P total. Then you have something P1 naught and P2 naught, alva. What do these represent is P1 naught na ನಾವು P total ದು minimum value ಅಂತ ಹೇಳ್ತೀವಿ as it is below. Okay. This above value, which is P2 naught, is the maximum value of P total. Okay. So how do you tell it overall? P1 naught is less than P2 naught. All right. Andre component 1 is less volatile anta artha. This is less volatile. This is more volatile anta when compared to P1 naught. So as of now, this is all about Raoult's law. Let's see what is ideal and non-ideal solutions. Okay. Yeah, I'll explain you in the other slides. But see, this is the basic example or basic plot of Raoult's law. Okay. I'll move on. Okay. Liquid solutions can be classified into ideal and non-ideal solutions. Okay. On the basis of Raoult's law, remember? On the basis of Raoult's law. If you consider ideal, okay, wait. Let's consider ideal and non-ideal. Ideal solution under very simple, the solution which obeys Raoult's law. Okay. And opposite to it, the solution which doesn't obey Raoult's law. All right. So this is the first and foremost important difference between ideal and non-ideal solutions. The solution which obeys Raoult's law is ideal solution. The solution which doesn't obey Raoult's law is non-ideal solutions. And you have other two important properties of ideal and non-ideal solution. Please look into it. The enthalpy of mixing. Enthalpy of mixing of the pure components. Okay. How do you tell it? Mix is 0. The enthalpy of, if you're taking notes, please note down. The enthalpy of mixing of two pure components is 0. Okay. Whereas here, enthalpy of mixing two pure components is not 0. All right. So next, last other property is this, the volume. Yeah, it is about volume. Mix. Wait, this is enthalpy of mixing. So this was volume is equal to 0. Whereas here, the volume of mixing is not equal to 0. Okay. Again, the ideal solutions have two other properties other than obeying Raoult's law and not. Other two properties are the enthalpy of mixing the pure components to form solution is 0. Whereas other property is the volume of mixing is also 0. Just remember the volume and enthalpy of mixing two pure components. That is important. You should mention pure components. As of now, just remember these three important types. I mean, these three important differences between ideal and non-ideal solutions. Let me directly move on to next slide. So ideal solution, you understood it, right? See what is enthalpy of mixing of pure components is given here. No heat should be absorbed or evolved during mixing. This is what it is 0 anta artha. And expansion or contraction agbardu. That means volume change agbardu anta artha. That's all. And examples are given here. Just look into it. I'll directly move on to next, which is non-ideal solution. And remember, non-ideal solution has two types, which is positive deviation and negative deviation. Okay, I'll tell you about them. You understood what is non-ideal solution, which doesn't obey Raoult's law, and which the enthalpy of mixing of pure components is not 0. Okay. Again, the volume of mixing is also not 0. These three are properties of non-ideal solution. In your exams, they'll ask you what is give a difference between ideal solution and non-ideal solutions, so that you should write these 4 points. Okay, the last point will be examples of them. That's all. And in non-ideal solution, you should mention that it has again two types of deviation, which is positive and negative deviation. As I showed you previously, you saw this graph, right? This graph you saw previously. Only this green dotted lines were present there. Do you remember? And you can see some purple lines above the lines, right? You have something like this, you have something like this, you have something like this. It is very simple to draw. Please observe, that's all. You have something like this. See, as it is positive deviation, that deviation will be above, like this, above this line, above this line, which is like this. Okay, this is what positive deviation diagram they'll ask you in your exams. Okay. And how do you distinguish this positive and negative deviation, Andra? Based on the higher or lower predicted value. Okay, solution. ಅಂದ್ರೆ ವೇಪರ್ ಪ್ರೆಷರ್ ಹೈಯರ್ ಇದೆಯಾ ಲೋವರ್ ಇದೆಯಾ ಅಂತ ಅನ್ನೋ ಬೇಸ್ಡ್ ಮೇಲೆ ಯು ವಿಲ್ ಮಾರ್ಕ್ ಇಟ್ ಅಸ್ ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್ ಆರ್ ನೆಗೆಟಿವ್ ಡಿವಿಯೇಷನ್. ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್ ಅಂದ್ರೆ ಏನಿರುತ್ತೆ? ಆಫ್ ಕೋರ್ಸ್ ಹೈಯರ್ ಇರುತ್ತೆ. ಸಾಲ್ಯುಬಿಲಿಟಿ ಸರಿ ವೇಪರ್ ಪ್ರೆಷರ್ ಹೈಯರ್ ಇರುತ್ತೆ ಅಂತ ಅರ್ಥ. ರೌಲ್ಟ್ಸ್ ಲಾ ಅಂದ್ರೆ ಆ ಗ್ರೀನ್ ಲೈನ್ ಆಗಿರುತ್ತೆ. ಆ ರೌಲ್ಟ್ಸ್ ಲಾ ಪ್ರಿಡಿಕ್ಟೆಡ್ ರೌಲ್ಟ್ಸ್ ಲಾಗಿಂತಾನು ಹೈಯರ್ ಆಗಿದ್ರೆ ದಟ್ ಇಸ್ ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್. ವೈಸ್ ವರ್ಡ್ಸ್ ಕೆಳಗಡೆ ಹೋಗಿದ್ರೆ ದಟ್ ಇಸ್ ನೆಗೆಟಿವ್ ಡಿವಿಯೇಷನ್ ಅಷ್ಟೇ. ಓಕೆ, ಇನ್ ಸಿಂಪಲ್ ವರ್ಡ್ಸ್ ಯು ರಿಮೆಂಬರ್ ದಟ್. ದೆನ್ ರಿಮೆಂಬರ್ ದಿಸ್ enthalpy of mixing pure components should be greater than 0 ಆಯ್ತಾ. And again, volume of mixing should be greater than 0. So remember these points and look into one example. They'll ask you example. And when you move on to next one, which is negative deviation, negative deviation. What do you see here? As I told you previously, you have a green line which is predicted Raoult's law. You have below that purple line is below that green line. That's why what do you consider it as negative deviation? And what do you say? It exhibits lower like vapor pressure is lower, which is exhibiting negative deviation ಅಂತ ಅರ್ಥ ಅಷ್ಟೇ. Okay, remember vapor pressure low ಇದ್ರೆ it is negative deviation. If vapor pressure is higher than the predicted Raoult's law, it is called as positive deviation. And again, ನೀವಲ್ಲಿ ಏನೇನು ಬರ್ದಿರ್ತೀರಾ, like mixing, look here, enthalpy of mixing pure components, ಅಲ್ಲಿ greater than 0 ಇತ್ತು, so it was positive deviation. ಇಲ್ಲಿ lesser than 0 ಇರಬೇಕು, that is the reason it is negative deviation. Also, the volume of mixing is also less than 0 ಅಷ್ಟೇ. All right. I'll move on. Other important definition is here, which is azeotropes. Okay. What is azeotropes? Have you ever heard before? I think no. Alva? If anyone knows what is azeotropes, you can text. You have live chats here. I could see some texts. Even if you are interested to answer, you can text, guys, so that we can converse each other and we can continue. All right, let me continue with azeotropes. Azeotropes are a binary mixtures. Binary mixture, again, only two components in a solution. Okay, are binary mixtures having same composition in liquid and vapor phase and boils at constant temperature. This is important definition for 1 mark. Okay, an azeotrope is a liquid mixture with a constant boiling point and vapor composition the same as a liquid composition. I would suggest you people to note this definition, which is not there in slide and which is important. A binary mixtures having same composition. Having same composition ಯಾವ್ದ್ಯಾವ್ದ್ರಲ್ಲಿ in liquid and vapor phase. In liquid and vapor phase also, and boils at constant temperature. Okay, this is a standard definition of azeotropes. So please make sure that you define this definition in your exams so that there will be no option to reduce your marks. Again, what is azeotropes? A binary mixture having same composition. Binary mixture having same composition in liquid and also in vapor phase and boils at constant temperature is what azeotrope is defined as. Again, remember some liquids on mixing will form azeotropes. Okay, again, what is azeotropes? It is shown. And azeotrope solution, it is not possible. You know, as I told you, it is a binary mixture, alva. It is not possible to separate the components by fractional distillation. Remember this point. It is not possible. Not possible to separate. Possible, sorry, spelling. To separate by fractional distillation. Okay, let it be. Something is happening. All right. Just remember, it is not possible to separate even by fractional distillation. This azeotrope solution is not possible to separate. All right. So again, let me move. This azeotrope again has two types. One is minimum boiling azeotropes, other one is maximum boiling azeotropes. Just remember two definitions. That's enough about what is azeotropes. All right. All right, it's not shown here. Let me move on. This the components cannot be separated by distillation, as I told you previously, when it is there here. Azeotropes, you understand what is minimum and maximum boiling azeotropes is. The solution which show large positive deviation from a Raoult's law is called as minimum boiling point. Wise words are there. Please understand and study. Alright? Minimum ಬೇರೆ maximum ಬೇರೆ. Where minimum ಅಂದ್ರೆ the solution which show large positive deviation from Raoult's law. Okay, this is what you have to define in your exam. And what is maximum? Maximum boiling azeotropes andre it shows large opposite to it. Simple negative deviation from Raoult's law at constant temperature. Aita. At a specific composition anta kuda helತೀವಿ. So just simple words ಅಲ್ಲಿ ನೆನಪಿಟ್ಕೊಳ್ಳಿ. What is minimum and maximum boiling azeotropes? Minimum boiling azeotropes ಅಂದ್ರೆ a solution large ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್ ನ ತೋರಿಸುತ್ತೆ. ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್ ಅಂದ್ರೆ ಏನು ಅಂತ ಮುಂಚೆ ನೋಡಿದ್ರಿ ಅಲ್ವಾ? ಎಂಥಾಲ್ಪಿ ಆಫ್ ಮಿಕ್ಸಿಂಗ್ ಮತ್ತೆ ವಾಲ್ಯೂಮ್ ವಾಸ್ ಗ್ರೇಟರ್ ದಾನ್ 0. ಗ್ರಾಫ್ ಅಬವ್ ಹೋಗಿತ್ತು. ದಟ್ ಇಸ್ ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್. ಸೊ ಆ ಯಾವ್ದಾದ್ರು ಒಂದು ಸೊಲ್ಯೂಷನ್ ಲಾರ್ಜ್ ಪಾಸಿಟಿವ್ ಡಿವಿಯೇಷನ್ ತೋರಿಸುತ್ತೆ ಅಂದ್ರೆ ದಟ್ ಇಸ್ ಮಿನಿಮಮ್ ಬಾಯ್ಲಿಂಗ್ ಅಜಿಯೋಟ್ರೋಪ್ಸ್. ಸಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಮಿನಿಮಮ್ ಅಂದ್ರೆ ಮಿನಿಮಮ್ ಪಾಸಿಟಿವ್ ಇದೆ, ಮ್ಯಾಕ್ಸಿಮಮ್ ನೆಗೆಟಿವ್ ಇದೆ. ಇದು ಸ್ವಲ್ಪ ಆಪೋಸಿಟ್ ಇರೋದ್ರಿಂದ ಪ್ಲೀಸ್ ಡೋಂಟ್ ಗೆಟ್ ಕನ್ಫ್ಯೂಸ್ಡ್ ಇನ್ ಯುವರ್ ಎಕ್ಸಾಮಿನೇಷನ್. ಮೇಕ್ ಶೋರ್ ದಟ್ ಯು look into this properly. And the examples are shown above. Just remember what is maximum boiling azeotropes. And then quickly let's move on to other things. ಸದ್ಯಕ್ಕೆ ಇಷ್ಟ ನೆನ್ಪಿಟ್ಕೊಂಡ್ರೆ ಸಾಕು. And look into these graphs once. Please take a screenshot and keep. And analyze it, okay? Okay. Other important concept is colligative properties. Okay, whatever is there in this chapter, everything is important which is there in this PPT. Only important concepts are being discussed in these sessions. Or simply we can tell it a synopsis of this chapter. Still deeper knowledge you have to gain. Okay. Quickly, let's see what are these colligative properties. Aita. Okay, let me start. Vapor pressure of a solution decreases when a non-volatile solute is added to a volatile solvent. Of course, alva. And tumba properties in the solution which are connected to, like which are said to decrease the vapor pressure. So vapor pressure decrease ಮಾಡುವಂತಹ ಕೆಲವು ಪ್ರಾಪರ್ಟೀಸ್ ಇದೆ. ಅದು ಯಾವ್ದು ಅಂದ್ರೆ ರಿಲೇಟಿವ್ ಲೋವರಿಂಗ್ ಪ್ರೆಷರ್. ಇಲ್ಲಿ ರಿಲೇಟಿವ್ ಬರುತ್ತಾ, relative lowering of vapor pressure. Okay. Next one is depression in freezing point, elevation in boiling point. Then you have something called as osmotic pressure. Of course, osmotic pressure. Osmosis andre ಏನು ಅಂತ ಓದಿರ್ತೀರಾ. Osmotic pressure andre ಏನು ಅಂತ ಇವತ್ತು ಶಾರ್ಟ್ ಆಗಿ ಓದ್ತೀರಾ. Okay, I'll move on. Time ಹೋಗ್ತಾ ಇದೆ. but we should not leave left behind, alva? Yeah, short agi, let's see what is relative lowering pressure. Okay. In simple words, how can we tell it? The vapor pressure of a solvent in a solution is less than the pure solvent. Okay, vapor pressure of a solvent in a solution is less than the pure solvent. So, or you can define this as well. When a non-volatile solute is added, its vapor pressure gets lowered. Vapor pressure कमी आता होगा. This is one colligative property. And you studied previously ಏನು ಓದಿದ್ರಿ ಇದು right? What was it? Raoult's law. What was this? Vapor pressure was directly proportional to its mole fraction, alva? That is what you have shown here again. XA na 1 minus XB. That is avagle ನಾವು X1 ತಗೊಂಡಿದ್ವಿ where we replaced with X1 minus X2. A, B ಅಂತ consider ಮಾಡಿದ್ದಾರೆ ಅಷ್ಟೇ. Then again, when you multiply P naught A with 1 and XB, this is deriving to this equation. And very simply, quickly, let's finish this concept. This formula is important in this part, that is relative lowering of vapor pressure. This P naught A minus P divided by P naught A is equal to WB by MB. Wait, in terms of 1 and 2 you study, guys. That will be easier, aita? I'll give you that equation right now. So before moving to that, I would like to explain what are these terms in the next videos. Okay, these terms will be explained further. So as of now, I'll give you what is that equation, which you have to remember. Right? Yeah, it's better to remember this. P1 naught minus P1 divided by, again, P1 naught okay, P1 naught minus P1 divided by P1 naught is equal to W2 into M1 divided by opposite to it, that is W1 into M2. Generally, you will have to find M2 in your normal calculations. Okay, in that calculation, just you interchange M2 with all these things. And in your numericals, they'll be specifying P naught, P1, P1 naught ಎಲ್ಲ ಏನು ಅಂತ ನಿಮ್ already ಏನು ಅಂತ ಓದಿದ್ದೀರಾ. So a question prakara, you have to identify what are these P1 naught value, P1 value, and W2, M1, W1, M2 values ಏನು ಅಂತ ಗೊತ್ತಿರಬೇಕು. Generally, you can see here W1, W2 ಎಲ್ಲ ಏನು weights ಆಗಿರುತ್ತೆ or simple mass ಆಗಿರುತ್ತೆ. Okay na? Whereas M1, M2 are molar masses of solute and solvent respectively. Respectively in the sense what I meant as respectively is 1 anta iradu, that is M1 W1 ಏನಾಗಿರುತ್ತೆ solute ಆಗಿರುತ್ತೆ, sorry, solvent ಆಗಿರುತ್ತೆ. Whereas 2 ಅಂತ ಇರೋದು solute ಆಗಿರುತ್ತೆ. Okay, so generally molar mass of solute na ನಿಮಗೆ find ಮಾಡಕ್ ಹೇಳ್ತಾರೆ in your numericals. All right, in that cases you shift all these transpose all these terms with respect to M2. Next, let's directly move on to next one. Yeah, next one is elevation in boiling point. Elevation in boiling point, and you will be more concentrating on water's temperatures. Okay, on temperature values ಮೇಲೆ ಜಾಸ್ತಿ concentrate ಮಾಡ್ತೀರಾ. Just remember TB ಅಂದ್ರೇನು? ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ಟೆಂಪರೇಚರ್ಸ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಓಕೆ, and remember delta TB is equal to TB minus TB minus TB not. Again, what are these terms? And you'll be studying in numericals so that you'll get proper clarification of what it is. Ebullioscopic constant is KB anta ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ. Again, you'll learn what is KB. Okay, now ಯಾಕೆ ಆ KB ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಂತ I'll show you the formula right over here. Okay, that formula is formula for elevation in boiling point, right? Elevation of boiling point ಅಲ್ಲಿ, of course they'll ask you to find the molar mass of solute particle. Then have difference and W1. W1, W2 are weights. Okay, and delta TB direct agi sometimes kodalla. In that cases, you have to calculate manually. How do you calculate it manually? As I told you previously, TB minus TB not ಮಾಡಬೇಕು. Why I'm stressing this delta TB andre, you have again further cryoscopic constant anta ಇದೆ. Okay, cryoscopic constant is again different concept in freezing point. Okay, I'll show you. Okay, show ಮಾಡ್ಬಿಟ್ಟು explain ಮಾಡ್ತೀನಿ so that you'll understand it properly. See, you have something called as freezing point depression. Andre, how do you tell it? Depression of freezing point ashte. Okay, ಅಲ್ಲಿ when you're giving the difference, you have here, which I was telling previously, adu I told you with respect to TB alva, because it was boiling point. As it is freezing point, you are taking as F anta ತಗೋತೀರಾ. And ಅಲ್ಲಿ there what you had, wait, I'll show. Delta TB is equal to TB minus TB not it. Here you have TF not first minus TF. Okay, this is what the major difference I wanted you to observe. So please concentrate on these differences and study so that you won't make mistake in your calculations. So remember this concept. Also, you have main formula for it, which is not here. I'll give you the formula. Yeah, please note this. M2. Again, molar mass find madak ಹೇಳ್ತಾರೆ. At that case, you should write this M2. M2 is equal to KF into W2. What is KF? What is KF? Any answer? Would you like to share? No? Okay. KF is cryoscopic constant. Okay. Where KB was ebullioscopic constant. Here it is cryoscopic constant. You have KF into W2 into 1000 divided by delta TF. There it was delta TB into W1. Same formula where only slight difference is there. Again, you should calculate this delta T have separately and you should substitute here. Okay. Again, for this explanation is enough. It's already time. Next is osmotic pressure. You know what is osmosis, alva? Just a movement of a liquid from one concentration to other concentration anta ಹೇಳ್ತೀವಿ through semi-permeable membrane. This is a general concept of osmosis, right? Flow of solvent anta ಹೇಳ್ತೀವಿ through semi-permeable membrane. And it was first, ಇದು ಏನು ಅಷ್ಟು ಇಂಪಾರ್ಟೆಂಟ್ ಇಲ್ಲ, just see the name. Abenollet ಅನ್ನೋರು found this concept, ಆಯ್ತಾ? And you can cell membranes ಅಲ್ಲೆಲ್ಲ ಆಗುತ್ತಾ, diffusions ಎಲ್ಲ ಓದಿರ್ತೀರ. As of now, I don't want to discuss those. Quickly, let me move on to the next one, which is osmotic pressure. Osmotic pressure. ಏನು osmotic pressure ಅಂದ್ರೆ? The pressure that just stops the flow of solvent. ಅಂದ್ರೆ osmosis ಅಂದ್ರೆ flow of solvent ಅಂತ ನೋಡಿದ್ರಿ. ಆ flow of solvent ನ stop ಮಾಡಕ್ಕೆ ಒಂದು pressure ಇದೆ. That pressure is called as osmotic pressure. How do you calculate this osmotic pressure? Again, you have numericals on this. Just look into the formula which I gave. Okay, note ಮಾಡ್ಕೊಳ್ಳಿ, it is better. You have M2. Generally M2 calculate ಮಾಡಕ್ಕೆ ಹೇಳ್ತಾರೆ. That is the reason you give M2. M2 is equal to W2 R and T divided by V. Okay, just remember this. Ella direct substitutions irutte. All right, where if at all osmotic, see what is pi under osmotic pressure? Sorry, I didn't mention that. Pi under osmotic pressure ಆಗಿರುತ್ತೆ. That is given in general cases. If it is not given, you should calculate manually. How do you calculate it? CRT ಅಂತ ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ. Just remember these formulas. When you see the problems, you'll understand where to apply, what to apply. All right. Quickly, I'll move on to the next one. Yeah, you have three types of solution on the basis of osmotic pressures. Hypertonic solution anta ಹೇಳ್ತೀವಿ, hypotonic and isotonic solutions. These things you would have studied in biology, alva? Just recall what is hypertonic, and isotonic. Hypertonic ಅಂದ್ರೆ ಏನು? Osmotic pressure high ಇರುತ್ತೆ ಅಂತ ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ. Okay, higher than what? Solution. Solution pressure ಗಿಂತ osmotic pressure ಜಾಸ್ತಿ ಇರುತ್ತೆ. That is where hypertonic solution comes into picture. Next, please remember this. You have something. First, you remember what is hypertonic solution. Then hypertonic solution cell na ಒಂದು cell you know ಅಲ್ಲ, cell ನ place ಮಾಡಿದಾಗ what happens ಅಂತ, fluid ಏನಾಗುತ್ತೆ ಆಚೆ ಬಂದ್ಬಿಡುತ್ತೆ. Cell ಇಂದ ಆಚೆ ಬಂದಿದ ತಕ್ಷಣ that whatever liquid was there in the cell that comes out ಅಂದ್ರೆ cell ಒಳಗಡೆ ಏನು ಇಲ್ಲ, so that will shrink. So ಆ cell ಇಂದ water ಆಚೆ ಬರ್ತದೆ, hypertonic solution ಆಗ್ತದೆ ಅಂದ್ರೆ that cell will shrink. Why I'm stressing this is, again you have a question based on this. Cell ನ ಈ ತರ ಇಟ್ಟಾಗ what happens, ಈ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಇಟ್ಟಾಗ ಏನಾಗುತ್ತೆ? ಸೊ hypertonic solution ಅಲ್ಲಿ ಇಟ್ಟಾಗ what happens? Cell ಅಲ್ಲಿರೋ ವಾಟರ್ ಎಲ್ಲ ಆಚೆ ಬಂದ್ಬಿಟ್ಟು cell shrink ಆಗುತ್ತೆ. Okay, and that concept is called as plasmolysis. You studied this in your biology again previously. If you are a biology student, easiಯಾಗಿ ಲಿಂಕ್ ಸಿಗುತ್ತೆ. If not, you have to recall what is this, or else simply ಇಷ್ಟು ಓದಿದ್ರೆ ಸಾಕು. Okay, hypertonic solution ಅಂದ್ರೆ ಏನು? Opposite of it. ಅಂದ್ರೆ ಒಂದು ಸೊಲ್ಯೂಷನ್ ಅದು ಆಸ್ಮಾಟಿಕ್ ಪ್ರೆಷರು ಕಮ್ಮಿ ಇರುತ್ತೆ ಆ ಸೊಲ್ಯೂಷನ್ ಪ್ರೆಷರ್ಗಿಂತ. ದಟ್ಸ್ ಆಲ್. ಓಕೆ, ಜಸ್ಟ್ ಲೋವರ್ ದಾನ್ ಅಂತ ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ. ಅಂಡ್ ಅಪೋಸಿಟ್ ಟು ಇಟ್ ಏನಾಗುತ್ತೆ ಅಲ್ಲಿ, ಸೆಲ್ ಇಂದ ಎಲ್ಲ ಸೊಲ್ಯೂಷನ್ಸ್ ಆಚೆ ಬಂದ್ಬಿಟ್ಟು ಸೆಲ್ ಶ್ರಿಂಕ್ ಆದ್ರೆ ಇಲ್ಲಿ ಸೆಲ್ ಒಳಗಡೆ ಸೊಲ್ಯೂಷನ್ ಹೋಗಿ ಸೆಲ್ಲು ದಪ್ಪ ಆಗುತ್ತೆ, ಸ್ವೋಲ್ ಆಗುತ್ತೆ. ಓಕೆ, ಐ ಮೀನ್ ಸ್ವೆಲ್ ಆಗುತ್ತೆ. Then you have something called as isotonic solution. ಎರಡು ಸೊಲ್ಯೂಷನ್ಸ್ ಇರುತ್ತೆ, ಎರಡು ಸೊಲ್ಯೂಷನ್ ಸೇಮ್ ಆಸ್ಮಾಟಿಕ್ ಪ್ರೆಷರ್ ನ ಎಕ್ಸರ್ಟ್ ಮಾಡ್ತಿದ್ರೆ ದಟ್ ಸೊಲ್ಯೂಷನ್ ಇಸ್ ಸಿಂಪ್ಲಿ ಕಾಲ್ಡ್ as isotonic solution. Okay, and another important point which I have to mention is remember more than less than 0.9 because this is asked more than 0.9. I'll tell you what it is. Less than 0.9. And yeah, ಏನಿದು ಅಂದ್ರೆ concentration. Okay, a percentage. Okay, so let's say the concentration of a solution is more than 0.9 under, that solution will be hypertonic. Remember this. More than ida andre it is hypertonic. Less than ida andre it is hypotonic. Okay. Then if the salt concentration is less than 0.9%, the solution is said to be hypotonic. Idu artha aitalva? So directly next, again ಏನಾಗುತ್ತೆ, water, I mean ಯಾವ್ದಾದ್ರು cell na if you place inside the hypotonic solution ಏನಾಗುತ್ತೆ ಅಂತ ಹೇಳಿದೆ, water will enter into the cell and that cell will swell. Okay, now directly to next one. See, this is what I told you. Cell in the water ಆಚೆ ಬಂದು cell shrink ಆಗಿದೆ. Cell shrink ಆಗಿದೆ in the sense ಏನಾಗಿದೆ ಅಲ್ಲಿ hypotonic solution ಅಲ್ಲಿ ಇಟ್ಟಿದ್ರು ಅಂತ. Whereas hypotonic solution ಅಲ್ಲಿ ಏನಾಗ್ತದೆ, cell ಒಳಗಡೆ all water is entering, all solution is entering into it. Okay, water enters into it if you are placing. Next, abnormal molar mass. What is abnormal molar mass? All right, last concept, abnormal molar mass. What is abnormal molar mass, guys? Again, time ಆಗುತ್ತೆ. I don't wait for the chat. ಇಲ್ಲಿವರೆಗೂ chats ಬಂದಿಲ್ಲ. Yeah, before moving into abnormal molar mass, one slide is missed here, which is all about of osmosis anta artha aste. Okay, the direction osmosis to direction na reverse ಮಾಡೋದು is called reverse osmosis. Very simple. Again, this is asked, so I'm specifying this concept. So understood alva? Generally what is reverse osmosis anta keltare. What is reverse osmosis andre ಏನು ಹೇಳ್ತೀರಾ? The direction of osmosis is reversed anta ಹೇಳ್ತೀವಿ, or the flow of solvent from higher to lower is there in osmosis ಅಂದ್ರೆ ಇಲ್ಲಿ lower to higher ಅಂತ ಹೇಳಬೇಕು, through semi permeable membrane ಅಂತಾನೆ ಹೇಳ್ಬಿಟ್ಟು you have to mention a example for it. Example ಏನ್ ಕೊಡ್ತೀವಿ, desalination of pure water ಅಂತ ಹೇಳ್ತೀವಿ. ಅಂದ್ರೆ purification, desalination of sea water, I'm sorry, desalination of pure sea water ಅಂದ್ರೆ ಆ sea water ನ purification process ಅಲ್ಲಿ we use RO ಕೇಳಿರ್ತೀರಲ್ಲ, reverse osmosis, that is what it is. Okay, as of now reverse osmosis ಬಗ್ಗೆ ಇಷ್ಟೇ ಹೇಳ್ತೀನಿ. Then I would like to tell this last concept, abnormal molar mass. What is abnormal molar mass? Again, the value of molar mass is either low or high compared to expected or a normal value. One value expect ಮಾಡಿರ್ತೀವಿ, ಅದಕ್ಕಿಂತ higher or lower ಬಂತು ಅಂದ್ರೆ that is called as abnormal molar mass. That's all. Okay, and ಅದ್ರದ್ದು ರಿಲೇಶನ್ಶಿಪ್ ನ ಕೇಳ್ತಾರೆ guys. This abnormality, ಆ abnormality ಯಾಕಾಗುತ್ತೆ, ಡ್ಯೂ ಟು ಅಸೋಸಿಯೇಷನ್ ಆರ್ ಡಿಸೋಸಿಯೇಷನ್. ಅಗೇನ್ ಅಸೋಸಿಯೇಷನ್ ಅಂದ್ರೇನು, ಡಿಸೋಸಿಯೇಷನ್ ಅಂದ್ರೆ ಏನು ಅಂತ ಹೇಳಿದೀನಿ. ಅಸೋಸಿಯೇಷನ್ ಇನ್ ದ ಸೆನ್ಸ್ ಕಾಂಬಿನೇಷನ್, ಕಂಬೈನ್ ಆಗೋದು ಅಂತ ಅರ್ಥ. ವೆರಾಸ್ ಡಿಸೋಸಿಯೇಷನ್ ಅಂದ್ರೆ ಸ್ಪ್ಲಿಟ್ ಆಗೋದು ಅಂತ ಅರ್ಥ. ಆಲ್ ರೈಟ್, ಸೊ ಆಸ್ ಆಫ್ ನಾವು ಅಷ್ಟು ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ ಸಾಕು. ನೆಕ್ಸ್ಟ್ ಯು ಹ್ಯಾವ್ ಸಮಥಿಂಗ್ ಕಾಲ್ಡ್ ಆಸ್ ವಾಂಟ್ ಹಾಫ್ ಫ್ಯಾಕ್ಟರ್. ದಿಸ್ ಇಸ್ ಇಂಪಾರ್ಟೆಂಟ್. ವಾಂಟ್ ಹಾಫ್ ಫ್ಯಾಕ್ಟರ್ ಅಂದ್ರೆ ಏನು ಅಂದ್ರೆ ಸಿಂಪಲ್ ಆಗಿ ವಾಂಟ್ ಆಫ್ ಫ್ಯಾಕ್ಟರ್ ನ ಐ ಅಂತ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತೀವಿ ನಾವು. ವಾಂಟ್ ಆಫ್ ಫ್ಯಾಕ್ಟರ್ ಇಸ್ ಡಿಫೈನ್ಡ್ ಆಸ್ ದ ರೇಷಿಯೋ ಆಫ್ ನಾರ್ಮಲ್ molar mass to the abnormal molar mass. you have 3 types of formulas. ಮೂರನ್ನು ನೆನ್ಪಿಟ್ಕೋಬೇಕಾಗತ್ತೆ. ಓಕೆನಾ? ವೆರಿ ಸಿಂಪಲ್ ಇದೆ, ನೋಡಕ್ ಮಾತ್ರ ದೊಡ್ಡದು ಅಷ್ಟೇ. ಅಂಡ್ ನಿಮ್ಗೆ ಅನದರ್ 1 ಮಾರ್ಕ್ಸ್ಗೆ ಡಿಗ್ರಿ ಆಫ್ ಡಿಸೋಸಿಯೇಷನ್ ಅಸೋಸಿಯೇಷನ್ ನ ಕೇಳ್ತಾರೆ. ಡಿಸೋಸಿಯೇಟ್ ಆಗಿದೆಯಾ ಅಸೋಸಿಯೇಟ್ ಆಗಿದೆಯಾ ಅಂತ. And yeah, see, first formula ಏನಿದೆ, ನಾರ್ಮಲ್ ಮೋಲಾರ್ ಮಾಸ್ ಬೈ abnormal molar mass. Normal by abnormal, very easy. Then observed colligative property by calculated colligative properties. Then you have something called as total number of moles of particles after association or dissociation, number of moles of particles before dissociation or association. In a simple ಇದೆ 3 formulas, so please make sure that you study all the 3 formulae. And last, less than unity. Less than unity andre, if I is less than 1, please note this, I 1 ಗಿಂತ ಕಮ್ಮಿ ಇದೆ ಅಂದ್ರೆ, if you see problems like questions related to this, and you will definitely understand what is this. So I is less than 1 ಇದೆ ಅಂದ್ರೆ we'll assume it as to be associated ಅಂತ ಹೇಳ್ತೀವಿ. Okay, association ಆಗಿದೆ ಅಂತ. Next, vice versa. I is greater than 1 andre, we'll tell it as dissociation. All right. Yes, guys, this is all about your Unit 1 solutions. I hope you enjoyed this session, and I would like you to attend more live sessions like this. And please support Sankalp Learning. This is all for the good learners. And all the numericals have been already uploaded in Sankalp Learning. Please make sure that you visit there. And yeah, nothing else to explain more. As of now, I would like to conclude, guys. Yes. Then thank you all. Hope you all enjoyed. And please keep supporting. And you guys keep growing and keep rocking everywhere. Please learn more, understand more. Please apply whatever you had studied. So whatever you study, application is very important. So I wish you all the very best for your future and your examinations, and concentrate and focus more on your studies only till this year completes. So by this, I would like to stop my session, and thank you for all for watching this video. Thank you.